In late 1873, Georg Cantor proved that infinity comes in different sizes. The counting numbers formed one level. The real number continuum stood above them. But Cantor could not settle the first gap in that ladder. Was the continuum the very next infinity after the counting numbers? Or could there be another infinity between those two levels? Could the gap conceal not just one missing level, but an entire hidden universe of infinities? Cantor believed the gap was empty, but belief was not enough. The question needed a proof, and the search for that proof would lead to an answer far stranger than Cantor's original question, an answer so unsettling that many mathematicians still disagree about what it means. His work on infinite sets helped give rise to a new mathematics, set theory. Infinity was no longer only a philosophical idea at the edge of calculation. It had become an object mathematics could organize, compare, and question. In 1900, David Hilbert placed Cantor's continuum problem first on his list of the great mathematical challenges of the new century. The first gap in infinity had become a test for mathematics itself. But before anyone could search inside the gap, they had to know what they were searching for. What would an infinity between infinities actually look like? To make the question concrete, choose a collection of points from the real line. Call that collection A. This is what any proof would have to test. Can A be placed in a list? If it can, then it is still counting sized, so it cannot live in the gap. But if A cannot be listed, the problem is not solved. It might already be as large as the whole real line. Some pieces of the line look smaller than the whole line, but still have the full size of the continuum. So a true middle collection would have to escape both known sizes, too large to count, too small to be the whole continuum. That was the object a counterexample would need to be. Cantor believed no such object existed. In 1878, he proposed that every infinite set of real numbers must fall into one of the two known sizes. Either it can be listed, or it already has the size of the continuum, nothing in between. This became the Continuum Hypothesis, but proving this meant proving it for every possible subset of the real line. Not one clever collection, every possible subset. Cantor could make the claim. He could even verify versions of it for controlled families of sets. But partial victories could not settle a statement about every subset of the real line. That is why Hilbert's challenge mattered. In 1900, he did not ask mathematicians to collect more examples. He asked for a decision. Either prove that every infinite set of real numbers has one of the two known sizes, or construct one set that sits strictly between them. One proof would show that the first gap was empty. One counterexample would put something inside it. But Hilbert's demand carried a deeper problem. He was asking what every possible set of real numbers must do, and set theory was still young. Mathematicians had often treated any collection they could describe as a set. Around the turn of the century, that freedom began producing contradictions. Before mathematics could decide what every set must do, it needed reliable rules for deciding what counted as a set. The contradiction that exposed the danger was Russell's paradox. Imagine the set of all sets that do not contain themselves. Now ask a simple question. Does this collection contain itself? If it does contain itself, then by definition, it should not contain itself. If it does not contain itself, then by definition, it should contain itself. The old freedom to create any collection had broken the system. Set theory needed rules. In 1908, Ernst Zermelo proposed axioms that restricted how sets could be formed. Later work by Frankel, Skolem, and others shaped the system now called ZFC. For this episode, ZFC has two jobs. It tells mathematics which sets are allowed, and it gives infinite sizes a ladder. The next infinite size after the counting numbers is called Aleph 1. Now, the continuum problem can be asked inside the rulebook. ZFC allows the counting numbers to exist. It also allows the collection of all their subsets. This is called the power set. Why does that matter? A subset of the counting numbers is just a sequence of choices. Include 1, leave 2 out, include 3, and so on forever. Those choices can be read as an infinite binary string, and an infinite binary string can code a point on the continuum. So the continuum problem becomes a sharper question. Does ZFC force the power set of the counting numbers to have the very next infinite size? The search had changed. It was no longer only about finding a strange set on the line. It was about whether the accepted rulebook of sets could decide where the continuum belongs. 38 years passed after Hilbert first posed the continuum problem on his list. No one had proved that the gap was empty, and no one had produced a set inside it. In 1938, Kurt Gödel changed the form of the search. Instead of trying to prove the continuum hypothesis directly, he asked whether an entire universe of sets could be built where the usual rules held and Cantor's hypothesis held with them. Here, a universe has a precise mathematical meaning. It is a complete domain of sets where the axioms of ZFC operate together. Inside such a universe, the counting numbers exist, their allowed subsets exist, and the continuum has a definite place on the ladder of infinite sizes. His target was ZFC holds, and the continuum lands at Aleph 1. Why would one universe matter? Because if ZFC could prove that Cantor was wrong, then every universe obeying ZFC would have to place the continuum above Aleph 1. So a single universe where ZFC held and the continuum landed at Aleph 1 would be enough to block such a disproof. The rulebook cannot forbid a universe that follows its own rules. The result would not prove that the continuum hypothesis was absolutely true. It would prove something subtler. As long as ZFC itself is consistent, adding Cantor's hypothesis does not break it. In other words, the usual rules could not disprove the continuum hypothesis. To do that, the universe had to be disciplined enough to control the continuum, but rich enough for ZFC to survive. He built it in stages. The construction begins with almost nothing. Then it grows in stages. At each stage, it looks back at what has already been built and admits only the sets that can be precisely described from those earlier objects. This is the key restriction. The door is not opened to every imaginable subset. A set enters only if a precise formula, using objects the universe has already built, can single it out. The rule has a simple shape. An object X belongs to a new set A exactly when X satisfies some formula, and that formula is allowed to mention objects already built in the earlier stage. So, among all possible subsets of what the universe already has, the next stage admits only the ones that can be defined by an exact formula using earlier objects as ingredients. For example, once the counting numbers exist, some subsets are easy to define. The even numbers enter by a rule. Take the numbers divisible by 2. The numbers below 100 enter by another rule. Take every counting number less than 100. In the actual construction, the formulas can be much more abstract, and they may use earlier sets as parameters. But the basic test is the same. The subset must be definable from what is already there. An arbitrary, endless selection does not enter just because it is possible. It needs a rule that the earlier stage can already state. The subtle part is that these rules become powerful over many stages. Even though each stage is restrictive, the whole construction is still rich enough for ZFC to survive. That is why this is called the Constructible Universe. The continuum is still being built from subsets of the counting numbers. But now those subsets are filtered by the construction. At first, this might sound too restrictive. If too many sets are left out, maybe the universe no longer obeys ZFC. But the proof shows that the rulebook survives inside it. And because the real number codes are admitted in such a controlled way, the continuum does not climb above Aleph 1. Inside the constructible universe, the first gap is empty. Cantor's hypothesis survives. In fact, Gödel proved a stronger result. The generalized continuum hypothesis holds throughout this universe. The crucial point is simpler. ZFC allows a mathematical universe where no hidden infinity appears between the counting numbers and the continuum. That settled one side of Hilbert's problem. The usual rules could not disprove Cantor's hypothesis, but they had not proved it either. The opposite possibility was still open. But Hilbert had not asked for one possible universe. He had asked for a decision. To decide the question from the usual rules, every ZFC universe would have to agree. So the missing half became clear. Could another universe obey the same rules, but place the continuum above all F1? That would make room for an infinity between the counting numbers and the continuum. The first universe had filtered subsets. The opposite task was harder. Add new subsets without breaking the rulebook. The difficulty was not simply adding a new set. A careless addition could collapse the ladder of infinite sizes, or break the axioms the universe was supposed to obey. The missing move had to be precise. Add enough new subsets to change the continuum while keeping ZFC intact. For more than 2 decades, that move was out of reach. Then, in 1963, Paul Cohen found it. He did not search for one strange set hiding on the real line. He changed the universe around it. Cohen's method is called forcing. The name can sound as if the rules are being pushed until they break. That is not the idea. Forcing starts with a universe that already obeys ZFC, then enlarges it carefully. Inside M, the counting numbers already exist. So do many old subsets of the counting numbers. The first universe filtered subsets. Cohen went the other way. He added new subsets of the counting numbers. But the new subsets could not be added casually. The old ladder of infinite sizes had to remain intact. All F1 and all F2 could not collapse into the same size. And ZFC still had to hold. That is what forcing was built to do. The method begins with something smaller than a set. It begins with a condition. A condition is a finite piece of information about the new subset. It might say, 1 is in, 2 is out, 3 is in, and everything after that is still undecided. A stronger condition keeps those choices and decides more entries. So forcing does not add the whole infinite subset all at once. It builds it through stronger and stronger finite instructions. Now, the old universe can state requirements for the new object. For example, it can require that the new subset eventually decide whether 100 belongs to it. Or it can require the new subset to differ somewhere from a particular old subset. In forcing language, these requirements are called dense. Dense means that no matter what finite instruction you start with, there is always a stronger one that passes the requirement. You can picture these dense requirements like checkpoints. A generic set is built by meeting every dense requirement the old universe can describe. When all those compatible finite instructions are put together, their union becomes one infinite yes or no sequence. That final sequence is a new subset of the counting numbers. It is not a familiar pattern like the even numbers or the primes, but it is not a careless addition either. It was built to meet every requirement visible from the old universe. That new subset becomes a new real number code. Then the old universe expands into a larger one, containing the old sets and the new generic set. The crucial point is that the rulebook still holds inside the larger universe. So the rules have not changed. The universe has. Cohen does not stop with one new real number code. For the continuum problem, the construction adds all F2 many controlled new codes. This makes the continuum at least all F2. Forcing also controls the other side. It prevents the continuum from growing beyond all F2. Now the hidden size appears, not as a familiar set with a simple name, as a consequence of where the continuum landed. all F1 now sits strictly between the counting numbers and the real number continuum. The first gap is no longer empty. This proved the other half of the independence result. If ZFC is consistent, then adding the negation of the continuum hypothesis does not break it. Gödel built a universe where Cantor's hypothesis survives. Cohen built a universe where it fails. The same rulebook permits both. Now, the result can be stated cleanly. Assuming ZFC is consistent, the usual rules of set theory cannot prove the continuum hypothesis, and they cannot disprove it. That was the shock. Hilbert had asked for a decision. ZFC gave a split. In one permitted universe, the continuum lands immediately after the counting numbers. In that landscape, the first gap is empty. In another permitted universe, the continuum lands higher. Now Aleph-1 has room to sit between the counting numbers and the continuum. The flexibility does not stop with this one example. Later work, including Easton's theorem, showed that the continuum can have much broader behavior within real mathematical constraints. Not every imagined value is allowed. The rulebook still has structure, but it does not force the continuum to sit in only one place. In compatible landscapes, the continuum can sit much higher. Then the hidden region is no longer one missing step. It becomes a long corridor of intermediate sizes. This is not a physical universe hiding somewhere. It is a mathematical universe. A complete landscape of sets obeying the same accepted rules, but placing the continuum differently. Cantor asked whether an infinity could sit between the counting numbers and the real line. Gödel showed the usual rules allow a universe where the answer is no. Cohen showed the same rules allow a universe where the answer is yes. So the original question did not disappear. It moved. The problem is no longer only whether the continuum hypothesis is true. It becomes a deeper question. Which universe of sets are the rules meant to describe? Some mathematicians look for new axioms that decide the continuum. Others take the independence result as evidence that many set-theoretic universes are legitimate. Either way, Cantor's first gap did not simply get filled. It revealed that the usual foundations of mathematics can hold more than one infinity landscape.